Hi, this is Jeff Spence, your Math 120 instructor for the Community College of Denver. And this is our video lecture over section 11.3, which covers our last counting technique called combinations. So combinations are very similar to permutations. The main thing in a combination is that order does not matter when we make these selections. So the first thing we need to do is distinguish between permutation and combination problems, and then we'll do some combination problems using the formula. So combination is our third counting technique. A combination of items occurs when the items are selected from the same group, just like a permutation. That's the same thing. No items are used more than once. That's the same as the permutation. But what makes it different from a permutation is that the order of items makes no difference. I wrote out some examples here. So when we're selecting committees, selecting books, cards, movies, or food. So let's say you're going on a trip and you want to select a few books from your book selection, or movies from your movie selection, or food from the menu. Order doesn't matter. But permutation problems involve situations in which order matters, like when we make passwords from left to right, a password matters. If we have rankings like president, vice president, secretary, or CEO, manager, stuff like that, or finishers of a race, first, second, third, order matters. Combination problems involve situations in which the order doesn't matter. Permutation order matters, combination order doesn't matter. The other big thing is that you're going to either use a permutation or combination is when you're not selecting an item again. No item is used more than once. That's a key thing. So combination and permutation problems, we select from a bank of things, and we select a certain number of things from a bank of things. It's just whether order matters or not. The multiplication principle that we covered in 11.1, you have different options at each stage, and you multiply the options at each stage, which is very different from selecting from a bank of things like this. So it says determine which involve permutations and which involve combinations. So 6 students are running for student government, president, vice president, and treasurer. The student with the greatest number of votes becomes the president. Second highest votes becomes the vice president, and the student gets the third largest number of votes will be the treasurer. How many different outcomes are possible? So this is where order matters. The person that gets the most votes gets president. The person with the second most gets vice president, and third most treasurer. So since order matters, we're using permutations in this problem. This would actually be 6 permute 3. And I'll actually do the math here. Let's see here. Let me get the calculator up. Pause this for a sec. So this problem, if you're selecting from 6 students and you want to know how many different ways we can get a president, vice president, and secretary, I think is the third one, then we do 6 permute 3. So 6, find the permute function, permute 3. There are 120 ways that we can get those 3 rankings, president, vice president, and secretary, from 6 students, 120 different ways. So this one says 6 people are on the board of supervisors for your neighborhood park. 3-person committee is needed to study the possibility of expanding the park. How many different committees could be formed from the 6 people? Here the order does not matter because it's just a committee, and in a committee it's just a group where everybody is equal. All right, and so if everybody's equal, there's no different roles. It's just 3 people in a group. So you're going to use the combination formula where you do 6 choose 3, and they'll do that on the next page here. Let me jump ahead to that. Or no, they won't do that. So I'll show that on the calculator now. 6 combination 3. There are 20 different ways that we can make those committees. Alright, so this illustration shows why permutations and combinations are different. So let's say we have 4 letters, A, B, C, D. We can compare how many permutations and combinations are possible if we choose 3 letters at a time. So we're going to choose 3 letters from 4 letters. Okay, we have a bank of 4 letters, and we're going to choose 3. So permutation, this top part shows you all the different permutations where order matters. These are all different. So we have 1, 2, 3, 4, 5, 6. 6 times 4, 24 different ways that we can select 3 letters from 4 letters. But if order doesn't matter, then we look at, like this is showing, these are all the combinations with just A, B, and C. These are all the combinations with A, B, and D. These are all the combinations with A, C, and D. And these are all the combinations with B, C, and D. And so there are only 4 combinations, but there are 24 permutations. All right, combination formula. This is the formal formula. If you're comfortable doing that, that's great. It'll show you in the next example, but you can still just use the function on the calculator like I've shown. So it says, we're saying we're going to form a 3-person committee from 8 people. So we're going to make, since it's a committee, we're using combinations. We're going to do 8 choose 3, which they show here is 56. They did the 8 factorial divided by the 8 minus 3 in parentheses factorial times 3 factorial. 8 minus 3 is 5, so that's how you get the 5 factorial. So they're going to take the 8 factorial down to 5 factorial and cancel it with the 5 factorial. So essentially it's just 8 times 7 times 6 divided by 3 times 2 times 1, and you get 56. However, if you want to do that on the calculator using the function, if the formula is too complicated for you, that's fine. So we would do 8 combination formula, not the permutation formula, 3, and we get 56. And that's totally fine. You just use the function if you're more comfortable with that. Okay. The last one is going to be a fairly complicated example where we're going to kind of mix counting techniques. So it says in December 2011, the U.S. Senate consisted of 51 Democrats, 47 Republicans, and 2 independents. How many distinct 5-person committees can be formed if each committee must have 3 Democrats and 2 Republicans? So first of all, we're making a committee. So if we're using a permutation function, or sorry, we're using the combination function, because order does not matter with a committee because everybody's equal in a committee. It's just a group where everybody has the same role. So the order of which, that's what they're saying at the beginning. All right, now they got to make sure they have 3 Democrats. So we're going to select 3 Democrats out of 51 Democrats. So that's why they're doing this 3 from 51. 51 choose 3. There's 20,825 ways you can do that. But we also need to pick the Republicans. Let me get this bigger, sorry. If we pick the Republicans, there are 2 Republicans out of 47. So 47 choose 2. There are 1,081 ways we can do that. So there's 20,000 ways we can select the Democrats, and 1,081 ways we can select the Republicans. And then, so those are different ways of selecting the Republicans, or different ways of selecting the Democrats. We have different options at each stage for selecting Republicans and Democrats, so we multiply those numbers using the fundamental counting principle to get the total number of ways of selecting this committee, 22,511,825. So this final problem is the most complicated one. It uses a mixture of combinations and fundamental counting principle, but it's a good one to look at. So that's it. Good luck. Make sure you go over mainly the order of understanding this part, if order matters or doesn't matter between combinations and permutations, and go back and check 11.1 on how to use the fundamental counting principle. Till then, we'll see you next time.